Good morning, my name is Li Wen, and I come from South China University of Technology. I am very pleased to participate in this year's IEEE SMC conference and to share academic achievements with all of you. Next, please allow me to share our team's recent research on robot teleoperation. The robot teleoperation system is the remote control of a robotic system by a human operator, allowing the operator to manipulate the robot and perform tasks at a distance. Due to the rapid advancement in robotics technology, telerobots are increasingly expected to be applied widely in diverse fields, including component assembly, ocean exploration, medical surgery, and space station maintenance. However, robot teleoperation faces several challenges. One of the most critical is how to equip the teleoperation system with the human stiffness. In this issue, previous research has developed advanced stiffness controllers, but these methods require operators to control position and stiffness simultaneously, which probably increase workload and lead to task inaccuracy and inefficiency. To address this, a feasible method is introducing learning from demonstration, or LFD, to transfer stiffness skills to telerobots, enabling automatic stiffness modulation. Several previous works tried to use learning from demonstration to transfer stiffness skills to robots, but they were still unsuitable for teleoperation due to their time-driven inputs and inadequate generalization ability. To overcome all these challenges, we propose a novel robot teleoperation system that combines the learning from demonstration to learn human multidimensional stiffness skills. In our system, teleoperation enables precise positioning guided by human operators, while learning from demonstration allows robot to automatically adapt its stiffness to various task environments. This is the framework of our proposed system. It consists of two main parts. One is the human stiffness transfer module. The other is the robot teleoperation module. As for the human stiffness transfer module, a teleoperation-oriented stiffness adaptive Gaussian mixture model and Gaussian mixture regression, or TOSA-GMM, GMR, is proposed to transfer human multidimensional stiffness skills to robots. As the stiffness is computed and analyzed on a Riemannian manifold and reference points are introduced, our method exhibits higher accuracy and stronger generalization capability. In order to cooperate with teleoperation, the robot stiffness is dynamically adjusted based on the initiative of operators. As for the robot teleoperation module, a variable stiffness torque controller is employed to ensure accurate tracking performance. Additionally, a single-leader dual-follower teleoperation strategy for flipping manipulation is designed based on task modeling. The operator can control two robot arms with a single-leader device to perform flipping objects, thereby reducing workload and improving efficiency. For the TOSA-GMM, the demonstration data, y, is concatenated by the position vector, x, and the stiffness of the human arm endpoint, kh. To enhance generalization, it is necessary to process the demonstration trajectories based on multiple observations. We select a set of reference points in the task environment, then transform the demonstrations from the base coordinate system into the coordinates of these reference points using equation 2. Hence, the proposed TOSA-GMM in the coordinate system of the RTH reference point is given in equation 4. The stiffness of a human or robot arm is represented as a symmetric positive definite matrix, so stiffness should be computed in Riemannian space instead of Euclidean space. To address this, we modified the GMM by transferring the calculation of the difference between the demonstration data and the centers of the Gaussian models from Euclidean space to Riemannian manifold space, as illustrated in equation 3. Furthermore, the parameters in equation 3 can be determined by expectation maximization algorithm, which aims to maximize the log likelihood function of equation 4. In the process of teleoperation, the TOSA-GMR is employed to reproduce the robot stiffness sequence based on TOSA-GMM. Instead of conventionally using time as the input, we use the position of the robot arm's end effector, xi, as the input. This allows the reproduced stiffness to adapt based on the user's actions, rather than being determined solely by the passage of time. Consequently, the reproduced data, its center and covariance can be written as equation 5. Hence, the TOSA-GMR in the coordinate system of the RTH reference point is formulated as equation 6 to 10. Finally, we fuse all the reference points as the actual output stiffness by weighted Karcher mean algorithm. For the robot teleoperation module, when performing conventional tasks, we employ single-leader single-follower teleoperation wherein the operator controls a single robot arm to perform tasks using a single-leader device. And a torque controller with variable stiffness is proposed in joint space as equation 17. And for cooperative tasks like flipping objects, in order to lessen operators' workload, a model-based strategy of using a single-leader device to control dual robot arms is proposed. Additionally, the torque controller 17 is employed in this teleoperation strategy as well. We validated our proposed system by performing two tasks: an electrical socket plugging in task and a continuous object flipping task. Here is the electrical socket plugging in task. In the demonstration stage, the human tutor was required to conduct the plugging in task 4 times, wearing an MIO armband on the left forearm, while the Kinect tracked the tutor's hand on the opposite side. We set the start point and the goal point as reference points and used the TOSA MMS with 6 Gaussian components to fit the demonstration data. In the teleoperation stage, we conducted 3 comparative experiments in this task. The first is the teleoperation with constant low or high stiffness. When using the low gain setting, the adapter failed to be plugged into the socket. When using the high gain setting, the task was successfully completed. However, the contact force was too high, posing a risk of damage to both the robot arm and the adapters. The second is the teleoperation with stiffness regulation, as referenced in an existing method. This method required the operator to wear the MIO armband and controlled both the robot stiffness and position. We invited 8 volunteers to perform the task. As a result, some volunteers were unable to complete the task, and the average completion time for those who succeeded was long. But with our proposed method, the average time cost reduced, and only 1 volunteer failed to finish the task due to lack of proficiency in using the TouchX. The third is the teleoperation with our method, but in Euclidean space. The reproduced stiffness ellipsoids exhibited apparently deformation around the start and goal points, this indicating lower accuracy and generalization ability compared to our proposed method. When using our method, it showed high accuracy, strong generalization ability, and user-friendly. Our proposed system showed high accuracy by effectively encoding and retrieving multi-dimensional stiffness on a Riemannian manifold. It also demonstrates strong generalization, performing exceptionally well across various adapters, starting points, and target points. Furthermore, it is designed to be user-friendly, allowing operators to simply control the position, which reduces their workload and significantly increases overall efficiency. Here is the continuous object flipping task. Similar to the electrical socket plugging in task, the human tutor utilized 2 MIO armbands to measure the stiffness of both hands and conducted the flipping task 4 times. A Kinect was responsible for detecting both hands' position. 4 reference points were established, 2 for the left hand and 2 for the right hand. To validate the generalization of our method, we performed 4 continuous flipping tasks. Boxes with different weights and shapes were used as the objects to be flipped. In the first row, for the task of flipping a 7 kg cubic box, the operator completed the first flip, and then used the button of the TouchX to set new reference points before the second flip. The remaining 3 additional experiments were conducted with small cube, cuboid, and cylinder-shaped boxes, respectively, further validating the effectiveness and generalization ability of our proposed method. It showed high accuracy, performing exceptionally well in dual flipping tasks. It demonstrates strong generalization by successfully flipping objects of various shapes and weights. Additionally, it is designed to be user-friendly, allowing the operator to control both robotic arms using just a single joystick, simplifying the operation process. Hence, according to the results of the aforementioned experiments, the TOSA GMR, which transfer human multidimensional stiffness skills to robots, can improve stiffness adjustment accuracy, enhance generalization, and it is more suitable for teleoperation. The single-leader dual-follower teleoperation strategy for flipping manipulation can reduce operator workload, increase task efficiency. We can conclude that our proposed system is capable of performing tasks that demand high positioning accuracy and stiffness adjustment. This is all of our research. Thanks for your watching.